Hi, good morning. Good evening, everyone. Am I audible?
Yes, sir.
Okay.
Yes, yes,
So,
audible.
so today we will be covering the first 4 weeks for quiz preparation. So this is going to be revision session. Okay, Vindan, over to you. Please start.
Yeah, okay. Thank you, sir. So we'll start the revision session for first quiz. So the first week, before that, any concerns, anything that you want to ask us? Or shall we move ahead to the revision session and after that you will be asking?
So one point I would like to add is if you have any questions from mock quiz also, those are also welcome.
Okay,
Yes, we
so
can begin and we can go to the end for to solve it.
okay, sure. So in machine learning techniques week 1, let me come to the topics that are covered. So the most basic thing that is covered in machine learning techniques first week is ML modular approach, and the whole week revolves around it. Okay, so what are the different steps involved in machine learning modular approach? They are training data, then model, then loss function, then optimization, and then evaluation. So basically we follow these steps in generally in all the machine learning modeling that we do. Okay, so we will cover all these one by one, all these steps one by one as covered in the week 1 as the revision session progresses. Okay, then the next important part which is covered in week 1 is the comparison between machine learning and traditional programming approach. So when to use machine learning, that is a question that is answered. So whenever we have no set rules available for a particular problem, we go with machine learning, or we can say when there is no step-by-step approach available, we go for machine learning thing. Right. For example, if you are going to do a basic addition of two numbers, so you know how to add numbers, or we can program it easily, right? So for such situation, we do not require any kind of machine learning. We can do it with traditional programming approach. But suppose you want to have a system where you are going to do some kind of speech recognition, like Alexa, or other such applications where there are no predefined well set rules, you go for machine learning. So this is the difference between machine learning and traditional programming approach. After that, let's move to the first
So actually,
part of
I had a question here. Should we take
yeah
it now or should I wait?
yeah, you can go ahead.
So when there are no set rules, at that time machine learning will help. So that is obvious. That part is clear.
Yeah,
But there are also some applications. Actually, this is what confused me in one of the activity questions in the first week. Even when there are set rules, you can still train machines, right? So
yeah,
it's not an
you are
exact
definitely
inference
correct.
kind of a, like you can train a computer to play chess with machine learning.
So see, even the traditional problems can be solved by machine learning, but that is like complicating the problem.
Yeah, okay.
I mean, when there
So
are set
when we
rules,
talk
why
about
to?
at this level, when we're talking about machine learning versus traditional programming, this distinction is has to be very clear, right?
Yeah. So even the traditional problems can be solved using machine learning, but sometimes it is like you are complicating the process. So if you can do it by traditional programming, then why to go for machine learning? That's the main question.
Got it. Got it.
Yeah. Okay. So the next thing is the first part of modular approach, that is training data. So basically, training data is something on which we are going to build our model for machine learning problems. So what it basically contains, it contains input and output. So input is nothing but a set of features or a single feature. It may be a single feature that you provide to the model, right? So these features are actually usually decided by domain experts. For instance, if you are solving a chemical problem, or you are so a chemical expert will suggest what are the different features which will be required to give me output. Okay, or if you are solving an electrical problem, then a electrical expert will tell me these particular attributes should be considered for solving this particular problem. So basically these features are decided by domain experts, and output are something the targets which we are interested in. Okay, so these outputs can be of two types. One is real or continuous numbers or discrete sets. Okay, so these are the two kinds of output that we generally deal with, and input contains features. Okay, now next thing, the representation. So this denotion that we use, x superscript I, that denotes ith feature vector. Okay, so I have left this t. It should be transpose of this. So different features stacked together, they form a feature vector. Okay, and what is this yi? This is the ith output label that we are going to use for training our model. Now together these xi and yi is represented by d, which forms our total training data set. So this whole training data set is basically divided into three categories: training set, validation set, and test set. So training set is something on which we are going to build our model. So our whole calculations and the whole modeling will based on training set. Validation set is the part of training data which we will use for hyperparameter tuning, or in MLF, as you studied, it is used for model selection. So what is this model selection? It is basically forming different models using different hyperparameters. So that is done by validation set. Next thing is test set. So after you validate your set, you train your set, you test on its unseen data. Why you do that? You do that for evaluation of your model performance, whether your model is behaving properly or not. So that is the work of test set. No questions in this, right? Or any question?
I just wanted to ask something, that it is not necessary that we have the training and validation exact, separate, right? Usually whatever data we have seen in the lectures, we have seen that only the training data is used for validation also.
Yeah, so see, when you are doing cross validation,
yeah,
in those cases validation set has no use. I mean, you are validating it then and there, but in general, these three sets we can use. I mean, this is depending on your approach that you are taking.
So I just wanted to say that test set has to be different, right?
Yeah, test set should be unseen totally.
100% different. But then training and validation, that can be like, we can just use some part of the training as validation, right?
Yeah, so if you are doing like this, you are doing it one-fold. You are not using cross validation, then you will have a validation set which is unseen.
Okay. Okay.
But if you are doing a cross validation kind of thing, then no need of validation set.
Okay. Yeah. Thank you.
Okay. So after that, the next part is
one question, Abhinandan. So are we using validation set for actual business problem or live data? Or we just need to do the training data and the test data to do all the calculations?
So in most of times we are using only training and test sets because we use cross validation mostly.
Okay, so we don't refer validation as a separate entity, right?
Yeah, so because we use cross validation, so validation set is not often used, but it is a part. We can use it if our approach is like that.
Okay.
Yeah.
So
and
one
I think in MLP, Srinivasan here, MLP, I think there was in the video, Professor Derek specifically mentioned, right? In charts, if we have created a validation set, the step was that combine train, select the model, the actual model that will work for you, combine the training and validation set, fit it, and then use prediction. So in case you have a separate validation set, at least that point said, you have to combine them and then run predict.
Yeah, so Swarnim sir, you have wanted to add something.
Yes, what Srinivasan said, I agree totally with that. So in our practices, training, validation, and test sets, the difference is quite distinguishable. In techniques part, since we mostly are applying our techniques on artificial data, so it might not make sense right away, but this is a very, very important point to keep in mind for working on real data sets, where test set, validation set, and training set, they make a huge difference. Please,
Okay.
go ahead.
Okay. So, sir, the next part of the modular approach is model. So what basically is a model? It is a mathematical relationship that maps input or features, because input contains features, to the output or label. Okay, so there can be different kinds of model that we prepare or build out of the training set that we have. So you can see the examples. For example, we build a model y equal to w0 plus w1 x1 plus w2 x2. So such kind of a model will be called a linear model, because here we are not using the squares or cubes of the features. So such kind of a model is called a linear model. Similarly, the second example, w0 plus w1 x1 x2 w2 x1 square w3 x2 square, such a model is a non-linear model that we map input to the output. So okay, so what exactly is model? We are actually finding w0, w1, w2. That is what we do essentially do while we form a model. Okay, so when we find weight parameters, we say we are modeling a particular training set. Okay, next thing is, depending on the nature of output, we choose our model. Okay, so if our output is such that it is real or continuous, we go for regression problems or the models of regression. And if we have output which is discrete, we go for models of classification. So this thing is also important that you should keep in mind. So in model, is there any doubt?
So we always calculate weights in terms of error and all these things, right? Always go for the
So
weight.
basically, modeling is finding weights.
Okay. And the plot which we draw between x and y, and the plot which we draw for weight means actually we need to plot for only weights, right? In terms of how optimal our model is,
so
not for x and y distribution.
Yeah, so the plots that you are using is between x and y mostly, inputs and the output. And you are using modeling technique to find these W's.
And we plot W as well, right?
So for loss functions, when you are doing optimizations,
yeah,
there you are using loss function with W.
So because that's a linear combination, that's why we always refer to that to just to have how optimal our algorithm is.
Yeah, so optimization is like out of all the models, the best model that you will choose or that you will be using. That is optimization. So for that, you need loss function, and then you find optimal W.
And also one of the lecture I saw that weight will always be linear, but your y and x can be a non-linear. So it will be always linear, right?
So basically, when sir said that in the lecture, it is like, for example, the second example, if you take, or the polynomial transformation. If I remember, it is in week 3, which sir has given this statement. So if you see this, if you consider x1, x2, so these are two numbers. So if when you multiply it, it will give you another number, right? Similarly, x1 square will be also a number. X2 square will be also a number. So let us consider this x1, x2 is 3, x1 square is 9, and x2 square is 16. Then this W0 plus this 4W1 plus 9W2 and 16W3 is a linear model between Y and W's. So in that sense, sir said.
But W can't be a binomial, means non-linear, right? I'm just asking, a different perspective. Do we have any scenarios where weight can be a non-linear?
No, I mean, we find
weight is a vector. So vector isn't linear or non-linear.
Yeah, we are basically finding these values, right? Even if you are saying
relationships are linear or non-linear.
Even if you are saying you are finding W1 square, even that is a particular number, right?
Okay, understood. Yeah, sorry. Yeah, I mixed that. You got it. Yes, combination will be the perfect. Yeah, thanks.
Yeah. Okay. So the next part, if we have no further question, we can move ahead. Next thing is loss function. So a loss function is basically a function which is calculating the disagreement between the actual and predicted values, where actual values are present in the training set and predicted values we are calculating from the model. Okay, so loss function is a mapping between actual and predicted values. So there can be different kinds of loss function. For example, we have sum squared error, mean squared error, mean absolute error, and so and so. Okay, and in case of logistic regression, we are using binary cross entropy. So there are different kinds of loss function. Depending on use case, we are using different kind of loss functions. Okay, these loss functions can be convex or non-convex. So if the loss function is convex, it is easy to get optima. But in case of non-convex functions, we have to use special techniques. This is about loss function. So why we are using loss function? Basically to calculate the difference between our actual and predicted values, how much model is agreeing to real scenario that we are finding using loss function. Okay, so any doubt on this?
Just
No.
a confirmation, was there a half in sum of squared errors generally?
Yeah, there is a half.
Okay.
Okay. Next part of the process is optimization. So what is optimization? Optimization is nothing but finding the ideal set of parameters or weights which minimizes the loss function. Okay, so in optimization, basically what we are doing, we are finding the weight parameters such that our loss function is minimum. So there are two ways in which we can do that. So one way is arithmetically doing that by using calculus, that is find the differentiation, equate it to 0, we call it normal equation method. The second way is finding it iteratively. So iteratively when we are doing, so we are basically in almost all of our algorithms, we are using gradient descent or some of its variation for finding optimal weight. Okay, so optimization is nothing but finding W such that JW is minimum. For this, you are plotting different curves, which learner was saying previously. Okay, so any doubt in this?
Just a doubt, sir. So basically, gradient descent, we may not really get, so we don't know what is the optimal value of the loss. So we just stop when we have reached the stopping criteria, right?
Yeah, so there are two criteria that you can use. Either you can use a particular error after which you do not want to go further, or you can use number of iteration as a measure. So two ways are possible. So if one of these criteria is met, you stop your optimization process.
So in real life, typically we do not really know whether we have actually reached the optimization.
Yeah, so therefore you are doing that to close the program. I mean, somewhere it should stop.
Okay, I just want to get that clear.
Yeah, okay. Next thing is evaluation. So in evaluation, what we basically do, we are checking the suitability of our model. So whether the model that we prepared is suitable for our case or not. So different metrics are used for this evaluation part. So we use different metrics for regression and classification. So for regression, we may use mean squared error, mean absolute error, and parameters like those, or root mean square. These parameters are used for regression case, and for classification, we use precision, recall, F1 score, or area under the curves of ROC or PR. These things we are using. Okay, so if our evaluation is not, I mean, when we are finding these metrics, and if this metrics is not satisfactory, then we do different things. Like we may add inputs or different features, or we can ensure that our data quality is better to get a better model, or we can try a different model altogether. For example, if we are using a linear model and if it is not giving us a good result, then we can go for a non-linear model, or we can go for polynomial regression if linear regression is not working. So we can try a different model, or we can go for loss, change in loss function. So see the values for which it is working properly, or we can adopt different optimization process if our model is not working properly in our for the test set. Okay, so this is what we do in evaluation. So if the matrix is working satisfactory, well and good. If it is not working satisfactory, we try different things. Any question in this?
Hello, Abhinandan.
Yeah, go ahead.
One question. Though in this section there was two curves. One is area under curve PR and area under curve ROC. So there were two different statements for the model effectiveness and model performance. What does it means what is the difference between effectiveness and performance? How we see it?
So we can say a model is performing well if it is effective. There is no, I don't think there is any difference in this.
Okay, there is no any such difference on these two statements.
No. So if something is effective, it is performing well.
Okay.
Yeah. So next thing is the machine learning taxonomy that we have used in first week. So basically in our course, we are covering supervised learning and unsupervised learning. Apart from that, there is semi-supervised and reinforcement learning, those two things. So our focus is on supervised and unsupervised learning. So in supervised, we have two kinds of models which are possible: regression and classification. Regression we use when our output is real. Classification we use when our output is discrete. So regression can be also further divided into a single label problem or a multi-label problem. So when we have only one output to predict, we call it single label. When we have more than one output to predict, we call it multi-label. In classification, again, we have single label and multi-label setup. So when we have single label setup, we can have a binary class or multi-class problem. Even similarly for multi-label setup, we can have binary class or multi-class setup. So I think here in multi-label and single label, there was a lot of doubt in week one.
So just one doubt. So
Yeah.
can you give examples for both labels and class for all of them? I just want.
Yeah. Okay. So suppose I have X and I'm calculating Y. Okay. So suppose based on some values, maybe for all positive values, we are taking Y equal to 1, and for all negative values, we are taking Y equal to 0. Okay. Positive and 0. For that we are taking. So suppose X is 1, then Y will be 1. X is 2, then Y will be 1. If X is minus 1, Y will be 0. And for minus 2, it will be 0. So such a setup where there is only one class, we call it a single class problem, and there is only one label, right? For each particular input, we have only one label, so it will be called a single label. Okay, so this is an example of single label setup. Now suppose we have a situation.
So there are two classes here, right? There is 1 and there is 0. There are two classes.
So
here.
it is a single label binary class.
Okay. Yeah. Okay.
Got it. Label is 1, but the classes are 2. So it is a single label binary class problem. Okay. Now suppose we have a situation where again we have some access, some features based on which we are calculating Y is like this. Okay. So Y is something like this, 0, 0, 1. So 3 possible labels we are calculating here: 1, 0, 0, and 0, 1, 0. Okay. So such a label where only one is possible, rest all will be 0. Okay. Such a thing will be called single
label multi-class.
Yeah. So it will be a single label multi-class, right?
Okay. Right.
And now suppose we have a situation where Y is like this: 1, 0, 1, 0, 1, 1, 1, 1, 0. Okay. So this will be called a multi-class multi-label problem.
So the last one, can you explain how there is 2 1s in this thing? Like we are using one out encoding for the above one. Here, what we are doing exactly?
Okay, basically, suppose you want to calculate. Let me give you an example. Suppose you want to predict.
Can you take that blood group, for example?
What? Fruit.
OAAB, and then positive or negative.
Okay, so I am not remembering what exactly you are saying.
And Brother, can we take that mock question, which is in the last question of, because we're confused with that same thing.
Okay, so let me take it. Give me a minute, I have to open it. So, Sunny sir, have you opened quiz, mock quiz?
Give me 1 minute, I'll open it.
Till that time, you can think it like this. Suppose I want to predict whether a given sportsman, cricketer, is a all-rounder or not. Okay, and we are taking three outputs. One is his batting average, next is bowling average, or you can say runs, wickets, and then catches. We are taking three things, right? So our all-rounder is classified as an all-rounder when he has runs marked as 1, wickets marked as 1, and catches can be anything, right? And if it will be like 0-0, then he will be considered as a not all-rounder. He will be considered not as an all-rounder. Okay. So we can have a case where 2 out of all possible outputs are 1.
Right.
Okay. So this is an example of this multi-class multi-label.
So here there are multiple classes such as wickets, such as bowling, such as batting, and
yeah. So different output classes possible are batsman, bowler, all-rounder.
Yes.
Okay. And features are and these are runs, wickets, catches, and some other attribute, maybe stumping, something else.
Okay.
Got it?
And multiple label because we'll have to represent it in threes, like.
Yeah. So our all-rounder will basically have 2 things positive. He is a batsman, he is a bowler. So 1-1. Got it?
Yes. Got it. Thank you.
So we will come to that mock question maybe soon. So it was not opened with me, therefore I could not go to it. So if it is clear, we can move ahead, right?
Yes, sir. Clear by my.
Sir, there was one more thing. I think it is in week 5. Not sure. I think it was multi-label indicators, something like that.
Multi-label indicator. Okay, so Swarnim sir, if you can comment on that. It is in week 5.
Multi-label indicator. Can you please expand or give me context of that?
I think it is in week 5, maybe 2nd lecture or 3rd lecture. There were 2 things: multi-class output and multi-label indicator.
Multi-label indicators. Okay, was it related to one-hot encoding?
It is in classification. Week 5 it is actually. Maybe the 2nd lecture.
Okay, Arshit. So maybe we can talk about that after this revision session.
All right.
Sure.
Yeah, okay. So next thing is ML models that we are using. There are different ways of classifying model. One is ways, if we are saying a model can be, ML model can be instance based. So when we say a model is instance based, when we are going to classify a particular unseen data, yeah.
Sir, can you please explain how will be multi-class and single label? One example on that.
Multi-class and single label.
Yeah.
So I can give you an example of that. So you are looking for a problem in which we have to do multi-class classification, but single label. Is that right?
Yeah, perfect.
Okay. So for example, consider you have, again, I'm giving just an example. We'll not go into how it will trained. So let's say you have a set of images in which there are 3 animals: cats, dogs, and let's say a pigeon. Okay. So every picture, there is only one animal present there. And there are 3 possible classes: cat, dog, and pigeon. So therefore, this is a multi-class problem.
Got it.
Yeah, and in each image, there's only one animal. Therefore, we have only one label for that image. Therefore, it is single label multi-class problem.
So basically, labels are the output. What labels indicate what will be the output, and classes will be the what are the possible outputs we have. What is the output set?
Yeah, you consider. Yeah, exactly.
Okay. Thank you.
Hello, Swamin sir. Swamin sir. Just one.
Yes.
clarification. If in that image there are, you mentioned particular case where in an image only one animal is there. If there are
Right.
more, then it is multi-label, right?
Yeah,
If
multi-class,
there are,
multi-label.
if there are images in the data set where a cat and dog or pigeon and dog or cat or pigeon or all three of them are present at the same time, we have to we have to figure out all possible. I mean, all three animals, if they're present, then it becomes a multi-class, multi-label problem. You're absolutely right.
Okay.
Yeah, it's just like finding all-rounders.
Right.
No, so it means that if based on the problem statement what we have, do we need to look for all the three elements or we need to look for one animals? Is it that's the case? For
Yes, that is right. Yes.
Okay.
Who also will do, right, sir? Two is also fine, no? For multi-level, multi-class. You mentioned that's why.
What do you mean by two?
If there's an image where there's a cat as well as there's a dog, both of them are there in the image together, then it is a multi-class, first of all, because we are covering all three animals, and multi-label as well, right? Just
absolutely.
Okay.
Yes.
Okay, so can we move ahead?
Yes, please.
Yes, sir.
So now ML models can be of two types, instance-based and model-based. So when we are finding the class of a unseen data based on the instances, by instances we may mean already present data. We call it an instance-based approach. For example, KNN, what we do in KNN that is going to come. I mean, in weeks to come, you will understand this. So basically, you have to remember this thing that we classify or we regress based on already present instances of a given data. We call it instance based. In model based approach, we have two further classifications, generative and discriminative. So when we are finding parameters of a particular model, I mean a particular distribution, for example, we have a normal distribution in which we have standard deviation and mean as parameters. So suppose we are finding this sigma and mu based on our data, then we are saying it's a generative model. Okay, so what will be the next particular data out of based on the previous data that we have seen? Such a model will be called a generative model. And in discriminative model, what we do, we basically learn the separators between two classes or between more than two classes. So we learn separators. So example of that is a logistic regression or SVM. So this is used in classification case. And example of generative is naive Bayes. So naive Bayes will be covered soon. Logistic, I think it is in week 5, and SVM will also be covered soon in our coming weeks. Okay.
So, sir, so discriminative is classification problem, and the first one is regression, is it?
No, actually, see what happens in case of generative. For example, there is when you type a message, so you see recommendations, right? What should be the next word, or so such a thing is called generative model based on the previous things that you have written. There is a suggestion, auto suggestion is there, right?
Right.
So such a thing will be called a generative model. So it is generating a particular instance based on the previous things.
Okay, this could be regression and classification both.
Yeah, so naive Bayes is used for regression, classification mostly. So generative models are something which you are finding the model of, I mean, you are basically finding a distribution and data can come out of it.
Can any simple example on discriminative, a practical example?
So suppose you are classifying, for instance, you are classifying positive numbers and negative numbers. Okay, then there can be one axis, x equal to 0. That is a discriminative thing, right? So anything which is greater than 0 will become positive. Anything which is less than 0 is negative.
Right.
So
And
this is
also, sir, in discriminative, we have to determine the decision boundary. That is the main goal, right?
Yeah. So basically, you are learning that decision boundary.
Yeah, sorry. Yes. The modeling is done for the decision boundary, right?
Yeah.
So then actually it is a classification problem only, right? We don't have regression problem there in discriminative.
No. So discrimination means classifying, right?
Okay.
So, but there are techniques like KNN which can also be used for regression also. So there are methods to it that you will learn soon.
So if I want to classify in terms of model-based So what will be my regression based models, or there something in the sense like what will be linear regression or lasso, sorry, linear regression in the sense, will it be in discriminative or generative?
So see, generative, mostly it will be generative, not discriminative.
So,
Since the error rates
Yeah,
follow
sorry,
normality, that's why you say.
sorry. So Tanvir, I did not understand your question. So you're asking whether Ridge and Lasso are going to be generative models or discriminative models?
No, so sir, he is basically asking out of these two models, which will be used for regression, generative or discriminative.
So like what will be the science model we select for regression based models like that? For regression, like for linear regression,
Actually,
what will
both can be used for regression and classification, right?
I mean, like in SVM, SVM basically works on both the principles, right? Regression as well as uh, classification sort of thing they have.
So that should be discriminative. So yeah, I mean, this is not classification versus regression. This is just type
No,
of, I think,
no,
learning.
but what will be if I want to say, if I have linear regression, so that learning for linear regression based model will be generative type of, or I'm not learning, I'm sorry. The modeling will be generative or discriminative. Because
Discriminative.
in mathematical
I think
sense,
that should be discriminative, right?
but in mathematical sense, the errors of linear regression follows normality. So we have PDFs for them. The whole actually whatever we are computing these numbers in or for example the errors basically in linear regression, they all follow normality. Hence we can do it. So that's why I'm always bit it seems very ambiguously what it is to me at least.
Okay, so before we get into this mathematically, so one idea that I could tell about discriminative and generative before going to the mathematical part is discriminative models only look for the differences. Think about it this one. So let's say if you want to distinguish between cats and dogs, so your model will only look at focus of the parts of the face of a cat or a dog where there is a difference. If all the images, all the data in the data set, all the images are like that, the dogs have collars and the cats don't have any collars, and that's true for entire data set, then discriminative model will figure out, okay, everything which has a collar is actually a dog, everything else is cat. So it will not look at the ears and any other feature of the image. That is one. I hope that makes sense.
Yeah, totally makes sense. I totally agree with you. But when you see it in that sense, it just gets sort of ambiguous.
See, for the regression, the model that you are talking about, I think logistic regression is a model which is a class which does classification, but it is derived from regression.
Yeah, okay. Also, okay. But for example, if I have California data set, I want to determine the price of the house. Okay.
Okay.
So what I'm using proper linear regression or sorry, polynomial regression or whatever regression I'm using. Okay.
Okay.
So what type of model that is? Is it generative or discriminative for me?
It's a no. So see, discrimination and generation comes into the play when we are talking about classification.
Okay.
So when we actually create a linear regression model, whether it is polynomial or not, it is actually drawing some boundary in the space, and logistic regression actually makes use of that fact that one side of the boundary gets positive, other side of the boundary gets negative. So it's a discriminative model. And now let me give an example of generative models. So generative models are, on the contrary, they try to learn about what actually a cat is, what actually a dog is. So it'll make a model how the eyes are different for cats and dogs, how the ears are different for cats and dogs, and so on. And whenever you give it a new sample, it will compare that new sample with cat model as well as dog model, and whichever model gives the higher score, that is the class of the sample. Okay, so it looks for the similarity between what models it already has.
Okay, thank you. So basically, when we talk about model, generative or discriminative models, we are actually talking about the, I mean, in the terms of classification only, right?
Yes, yes.
Okay, thank you.
So in the interest of time, can we move on to questions? So we're still in week 1, right?
Yeah. So can we move ahead?
Yes, please, sir.
Sure.
Definitely, definitely. Yeah.
Yes, sir.
Yeah.
Yes.
So the next step which was covered in week 1 was cross-validation. So what basically we do in cross-validation, we divide the whole set into k parts. Then out of those k parts, we use k minus one part for training and remaining one part for testing. Okay. And then the evaluation metric that we are using, it may be accuracy. We average over all the k partitions, I mean k partition. Okay. So this is what we do in cross-validation. Next thing is pre-processing. So there are different things which are covered in week 1, like normalization. So basically you are scaling your all the features between 0 and 1. So that is what we call normalization. Then conversion to numeric values. For example, there is an image. So what we basically do, we break the image into pixels. So on while doing that, what we are exactly doing, we are converting the image into numbers. Okay, next there was something called missing values. So how to deal with these missing values? Suppose there are some blanks in the feature values. Okay, so two ways we can do it. We can either remove the missing values, or we can take an average of the feature value for which the value is missing. Okay, so if we remove the that particular feature or that particular example, then we are reducing the number of data. So that is not sometimes which is not good. I mean, if already our data set is of low quantity, then that is not good. So taking average feature value makes sense in such cases. Next problem which was discussed was class imbalance. So what is class imbalance? If we have a training set such that there are too many examples from one particular class and there are too few examples from other class, we call it class imbalance problem. Okay, so to deal with it, and all those things are going to come in the weeks to come. Next important thing covered was gradient descent. So there are different forms of gradient descent: normal gradient descent, mini batch gradient descent, and SGD. So what basically is the process of gradient descent is already covered in MLF course as well, right? So basically you are taking the weights and then you are finding the derivative of the weight, and then you are finding the distance, steepest distance direction, steepest descent direction, and then you are doing wk plus 1 equal to wk minus alpha dou j upon dou w, right? So that you are doing in case of gradient descent, which we have already studied in MLF. Next is the learning rate. So learning rate is basically you are multiplying your the derivative that you are calculating at a particular point. So how big step you are going to take for updation, that is determined by learning rate. So if your learning rate is too large, what happens? You overshoot your optima. And if it is too small, then what happens? The convergence is very, very slow. So how to decide alpha? That we do using learning curve. So learning curve is also covered very extensively in week 1. So you can see that from the lecture. So a learning curve is basically the curve between loss and the number of iteration. Okay, so that you can see. Next important thing covered in week 1 is overfitting and underfitting. So overfitting happens when there is a situation where our model is trying to cover all the points in the given training set. So it behaves very good for training set, but when the unseen data comes, the loss is very high. So such case is called overfitting. To reduce overfitting, there are two methods. We can use more data and we can use regularization. These two steps can help in overfitting. For underfitting, what happens? Our model behaves does not behave good in case of training as well as testing. For both, the losses are high. So such a case is called underfitting. So for underfitting, there are two ways to deal with it: either add polynomial feature or reduce regularization. So any doubt in this?
Not in this. You talk about gradient descent, but mini batch and stochastic gradient descent, the samples which we pick, can you just talk we select K samples, right, for mini batch?
Yeah.
K
So
batches.
see what happens in case of gradient descent. Suppose in normal gradient descent, what happens? We are calculating derivative of all the points, okay, and then we are finding the weight updates of all the points by computations, right? So that is a very lengthy process. It takes a lot of time. So what happens? We can do what? We can divide the whole this training set into K different batches. So we are taking small sets and we are updating those sets at a time. We are not doing for every point. We are doing only for those K points. So that is called mini batch gradient descent. And suppose the batch size become 1, then we call that mini batch gradient descent as stochastic gradient descent. Therefore, yeah.
So one is actually you are referring for one set, one sample, right?
So in normal gradient descent, suppose in X, we have 1,000 examples, okay, in total 1,000. And if we are doing for all these 1,000, then we call it normal gradient descent.
Right.
Okay. Suppose I divide it into 50 parts, then what will happen? I will divide 1,000 by 50. So 20. It will be 20, right? So
20,
this
60.
will be called mini batch.
Right.
And now suppose I divide this 1,000 into 1 parts each. So I will do for one example. Then I will call it stochastic gradient descent.
Sorry. So for 1,000 you divided into one set, complete one set as 1,000, right?
So you are doing updates of each individually in case of
right.
stochastic gradient descent.
So this is like what we do in Perceptron.
Yeah. Yes, Jaideep.
Basically, we are training 99 data and then updating on the 1,000 data in iteration.
So your computation time is saved. A lot of computation time is saved when we are using stochastic gradient descent or mini batch gradient descent. So I think sir has covered that part in collab by taking time as well.
But sir, speaking theoretically, stochastic gradient descent will require more time, right? Because it is going to do it n number of times or n minus 1 number of times it's going to train the model.
No, but it will only train it once. Nah, it's like I'm doing for the 7th step. I have already done computation till the 6th step. So I have to just compute it one more time.
Yeah, so one time each happen, right? When you are doing it for this normal gradient descent, you are actually updating it same times and then you are moving to the next iteration. So every time it goes on adding.
Okay.
So for there, it is like if it's 10 data sets, so it will be 10. And for example, if you're on the 10th one, 10. So it will go to 100 times. And here you have to do only 10 times.
Yeah.
And for mini batch, how much ever the batch is like that.
Yes. So this is the gradient descent part. Overfitting, underfitting, I think it must be clear by now. So if I have a situation where I am trying to replicate all the data points like this, I call it overfitted. Because if there is a data which comes here, I don't know, this prediction will be very, erroneous, right? And underfitting happens if we have a situation like this, we are not following the different data points. Okay, so here what happens? Training loss is low and test loss is high. And in this case, training loss and test loss both are high. Okay. So next thing is some part of week 2 also I'll cover. After that, Swarnim sir will take over. So what is so in week 2 we start with regression, right? So first thing, what is a regression? Regression is a supervised learning model where our output is a continuous label, right? So there are different kinds of regression like single label and multi-label. When your target output is only one, we call it single label, and when we are calculating more than one, we call it multi-label. Okay, so this is the distinction that is covered in the week 2. Next thing is feature matrix, which is covered in week 2. So I think by now you people know what is feature matrix. So suppose I have a training example. So that training example will consist of different feature or attributes. So when we stack those features together, we call it a feature vector. And all the feature vectors for all the training examples, when we keep in a matrix where each feature vector is transposed and kept as rows, we call it a feature matrix. So basically the columns represent the number of attributes or the number of features present in the input, and the number of rows will represent the number of examples present. Okay, so this is what is feature matrix. And then there is Y, which is output label vector. So it will basically consist of Y values for different given training examples. So here again, column will represent output of each, and rows will represent number of training examples. Okay, this is about training data. The next thing is model. So regression model, in this case we are considering linear regression for week 2. So model will be something like this: y equal to w0 plus w1 x1 plus so and so wm xm. Okay, so these w's are nothing but weight parameters, and these x's are nothing but features, and y is the output. Now since here we are using no quadratic term, we call it a linear regression model. Okay, next thing, for a given number of features, we need, suppose we have one feature, then our equation is something like this: mx plus c, right? So for here we want to learn m and c. So m and c are what? Parameters, right? So for feature equal to 1, or I can say number of feature equal to 1, I need 2 parameters to learn the model. Similarly, if we have more than one feature, so I can write the equation like this: a plus bx1 plus cx2. So for 2 features, we need 3 parameters. Or in general, what happens for m features, we require m plus 1 parameters. Okay, so we can write this equation in vectorized form as wixi I equal to 1 to n. So basically it will consist of a dummy feature plus all other features. So a dummy feature is added to account for w0, which is present in the model. Okay, so we write it like this: y equal to w transpose x, where w will represent weight vector, x will represent feature vector, and y is the output.
I should be ranging from 0, right?
What?
That summation I should be ranging from 0 or 1?
Sorry. I should be starting from 0. Correct. Okay. Next thing is loss function. So loss function, I think we covered in MLF as well. So loss function that we used for this linear regression model is basically sum squared error we are using, or least square error we said it. In case of MLF, we are calling it least square error, right? So what it basically is, it is nothing but EI is equal to Y I minus y hat I whole square, right? So where y hat is nothing but predicted values and y is actual values. So when you sum it over, you will get the total error E, which is nothing but sum of all the EIs over I equal to 1 to n. Okay, so and then you have a half over here. So if you write it in matrix form, you will basically get half okay. So this we have already seen in MLF as well. So I think it is clear with you. So this E is called as JW or the loss function.
I have one doubt here. Y hat is the predicted one, right? Although we are squaring from the notation point of view, y hat should be first one, right? Because XW is the prediction.
Yeah, okay. So you can write it as predicted. So if you do like this, so this is for your knowledge only. If you are doing like this will also give the same thing.
Yeah. Okay. Notation. Yeah. Because we are squaring, it
So
doesn't.
if you are writing like this, it is predicted minus actual.
Yeah.
That is fine. And this is actual minus predicted.
Yeah, it
So
doesn't
you-
matter. It's square, na. Anyway, we are doing
Exactly.
Yeah,
Yeah, it
no.
doesn't
So
matter.
in terms of to maintain a consistency, this is a valid point.
Yeah.
Yeah, perfect. In the course, we have honestly used everywhere predicted minus actual.
Yeah. So for in terms of consistency, predicted minus actual. Yeah. So this should be predicted minus actual. So any doubt in this?
Sir, don't you think the first expression y minus hw, if I am writing y minus hw, the second expression should also be y minus hw? We can't write it the other way because suppose the first element of y minus hw is minus 4.
Yeah.
The next minus xw minus y will become 4. If I multiply them, if I take a dot product, I'll get minus 16, not 16.
No, you will get
but
16.
My intention is to get
16 only. See why you will get 16? Because in both there will be minus 4.
Actually, I think it's a mistake in the first step. That's it. I think it should be xw minus y in the first one.
Y minus xw will also.
Upper
one.
Oh, okay. Sorry.
This one, yeah.
Yeah. Got it. Okay, this was my mistake. Sorry. So it should be xw minus y only. Thanks for the correction. Any other doubt?
Well, I have a big doubt in the next part when we talk the derivative part. So I'll ask you that.
So I think if there is no other doubt, so Swarnim sir, you may continue from here.
Okay, Aminan.
Okay, thank you.
Is my screen visible?
Yeah, sir. Yeah.
Yes.
Okay. So thank you, Abhinandan. So Abhinandan has covered till now what is the loss function, what is its expression. Now comes the point we move forward towards optimization. That is, now we want to find a fitment or a model for which the loss function is minimized. So I'm going to use the slides that Sir has used for quickly moving forward. So some of the identities which are required to derive a model for loss optimization for loss function, these are provided here. And this is the derivation of the loss function. Now here, as you can see, I see. The function that I'm trying to look for is the. So it is actually highlighting more than I wanted to. But the first line is actually what Abhinandan has written just a few minutes ago. And what we want to do is we want to find the optimal parameter set, which is W. And that's why we want to partially differentiate our loss function with respect to W. And this is the entire procedure. Sir, you said you had some doubt. Is it regarding this one or the next?
No, after that, when you go to the implementation of it.
Okay, sure. And so this is the entire procedure of finding the derivative. And this is the final expression that we get. So this is worth keeping in mind.
So when we write this into code, we just say P inverse of X minus Y.
So yeah, I'll come to that part. So right now we have derived the partial differential of loss function with respect to W. Now, in order to get what is the optimal value for W, we have to equate this to 0 because at that point the loss should be minimum. Right? So once we have calculated the derivative, there are two ways we can move forward. One is normal equation, and the second one is gradient descent. So first, let's look at the normal equation. In that part, what we do is we just readily equate our loss derivative to 0. So by equating it to 0, we get a point where the loss should be minimum, right? And this is how we get it. So this is actually your final answer. So do you have questions regarding this?
Yeah, so now when we write a code for this, even Sir has used that now just say np dot linear P inverse X at Y, right?
Yes.
In
yes.
section in SWI 4, right? Jimmy kind of wrote that entire part. And I tried both of them. They work the same, but I couldn't figure out the mathematical part.
I see. So see, internally, this P inverse represents pseudo inverse. It is used for matrices which do not have a square shape, especially for those. So either we can use directly P inverse, or we can write X transpose X, inverse of that, and then multiplied by X transpose. Both of them are actually same.
Okay, in section 4, I think maybe I can get help from others also. Jimmy used P inverse for all of them multiple times.
P inverse of all of it.
Yeah, so he X transpose X, P inverse of that. So that's why I got a bit confused. But the results come out to be the same. So mathematically, I wasn't sure how to.
P inverse is basically for inverse for matrices where we have no full rank. The invertibility is not sure. Yeah, they are just we have done SPD. If you have done obviously you have done MLF, right? So in the middle of the MLF, the inverse which we get is kind of the pseudo inverses.
No, I understand what P inverse is. Okay, let me just ask the question directly, right? So suppose I have to write this in code. So what would I use? I'll say W equal to pseudo inverse of X at Y, right?
Numpy dot linear algebra dot P inverse PINV of X
at Y
multiplied by Y. Yes.
Okay, so let me copy paste. Let me try to show the code that Jimmy used in week 4. So that is, he was using it multiple times. The code, then I will ask.
Okay, sure. So while sir, you're doing that, may I move forward?
Yes.
Yeah. So the other method for which we can actually by which we can get the best set of parameters is the gradient descent, which is a more iterative method, and it is very, very useful for data sets. See, for this normal equation method to work, you are computing this particular expression, and for that you are taking the entire feature matrix as well as label vector into your memory. So this is very, very good or suitable for small data sets. For any larger data set, this method is not going to work. Okay, and for that case, we need gradient descent. So what do we do in gradient descent? First, we randomly initialize the weight vector W. You could initialize it to 0 also. Then compute the gradient loss with respect to the weights. So this one, in this particular expression, you can see that we are calculating loss with respect to individual weight parameters. So this is non-vectorized version of gradient descent. In this one, what we do is the alpha is the size of your step towards the minima. So this quantity represents the direction in which your function is growing with respect to W, 0, right? So what we want to do is we want to go into the opposite direction. We want to go in the direction where loss is decreasing with respect to W0, and that's why we add this negative sign. And how large a step we want to take in? We want to take a small. The size of that step is controlled by this variable, which is alpha. So this is what we do for each and every parameter weight. And what we do is whatever the previous version was, we subtract this small. We take a small step in the negative direction by subtracting this quantity from the W0 in previous iteration. And similarly for all Ws. One point to keep in mind is generalize in the original version of the gradient descent. You do not update the parameters one after the other. You update them simultaneously. What I mean by that is we calculate this. We calculate our new W0. We calculate our new W1 by the previous value of this derivative. Okay, so in this one, we don't have the updated version of updated value of W0. This is what this slide says. This version has been non-vectorized and therefore not very quick to execute. Now, this one is actually vectorized. This one. So Wk represents the weight vector at kth iteration, and Wk plus 1 represents the updated weight vector. And capital X, capital Y, and small w, they are respectively the feature matrix, label matrix, and W stands for parameter vector. So in this way, writing in a vectorized method, we can get all the updated weights in a single line of code. Now, how does this loss function look like, and what actually gradient descent does? This is depicted by these two diagrams. So on the right hand side, you will see a contour diagram, and the left hand side, you see the 3D diagram. So the loss function that we are working with is sum of squared error. It is convex by nature. So you are going to get a bowl-like shape, something like which is depicted from in the left hand side. And on the right hand side, the same chart is being represented, but on a 2D contour plot. So the lower the value of the loss function is, it is going to be blue. So at the center of where the star is, actually that is the smallest value of loss function. And what we want to do is we want to get there. Every point on the loss surface is actually going to be a model. These are some of the properties of gradient descent. I'm going to skip them. Yeah, so before we move on, there is this very important part, which is alpha, which is the learning rate. And the second important thing that we need to decide when we are training our model is number of iterations. So this was an animation. If you remember, so slowly and slowly, sorry. Okay, I have to stick with our highlighter. So let me increase the font of, yes, I think this should be clear. So this initial dot represents the dot, the original or the initial weight vector that with which we are starting our training with. And every time what we do is we are going to take whatever the steepest descent is presented from that point. So it might be over here, and we on the next point we go forward. Similarly, we keep moving until we move to our minima. So this, how large or small our step is, it is being controlled by alpha, which is our learning parameter or learning rate. And this is very important point for all real world problems where the number of features are more than 2. It is not possible to actually visualize these loss functions. Now, this alpha, which is a regularization rate, it is a very important parameter, and it can decide whether our training is happening smoothly, happening at all, or actually we are moving away from our optimal solution. So in these 3 charts, for the particular loss function that we saw in the previous slide, for small values of alpha, for example, 0.001, let's talk about this one. You can see that after 40 iterations, I mean, even though error rate is decreasing, it is decreasing nicely, but it is decreasing slowly. So you can see that even after 40 iterations, there is some amount of error. On the contrary, if the alpha, the learning rate is slightly larger or more appropriate, what happens is the loss function drops very quickly and plateaus. That means there is not much change. That means we are learning much more quickly as compared to a smaller learning rate. But what happens if we put a very large learning rate? What happens to our gradient descent algorithm? It might actually start diverging. Okay, so maybe I should go in the previous slide and explain this one. Yes, so what happens if we take a very large value of alpha? Let's say if I start from here. So if I start from here, I take a very large step. Instead of going, near to my optimal solution, I go overshoot it, possibly. And from here, if I run again, if I take a very large step, what is going to happen is, again, I'm going to overshoot it. So what will happen is I will keep overshooting my optima, and every time after every iteration, my model will be actually further away from my ideal model.
Sir, I have a conceptual question here.
Sure.
For the value of alpha equal to 0.5, can you go to that diagram again?
Sure.
Loss
Yeah,
learning
sure.
curve.
Yes, tell me.
No, the learning curve. Alpha equal to 0.5. There are 3 learning curves. Yeah, this one, the third one.
Yes.
What is implied by the third learning curve is that right after the first iteration, when the weights are updated for the first time, at that point we are overshooting the optimal W.
Yes.
But it might so happen that for the first few steps, the loss might reduce because we haven't reached the weight, and then after maybe five or 6 steps, we have overshot the optimal W. Then the loss function will increase. So we might have a convex shape for loss function. Is that possible?
No, that is not going to be possible because alpha is actually, being multiplied to your this quantity.
Derivative.
Derivative, right? So see, if we are moving closer, then the third case will not be possible at all. We will only have either first or second case. Only if we alpha is large enough that we are overshooting from the first step, we are going to get the third curve.
Okay. Decrease and then increase. It will always be a monotonically decreasing or increasing curve, right?
Yes. Or I mean, theoretically, it is possible that you are jumping between only two values, which will cause you to oscillate plateau. I mean, the curve would look like a flat line, but you are not actually learning anything.
Okay. Thanks.
Yeah. Now, the same concept that we discussed just now, they are being described in the following slides. Now we'll come to the part where we will study the distinguished variations of gradient descent. I think Abhinandan gave them a great introduction. So the first one is the original one, which updates the weights only after going through the entire data set, or I should say entire training set. Mini batch, what it does is it divides the entire training data into small batches, and for every batch, after going through every batch, it updates the weight vectors. So this way, the weights are updated more quickly, and that is why mini batch gradient descent moves towards makes more movements for the same number of training samples. And the next variation is so this is more details. So see, your K is very, very small, which is the number of batches. Okay, so let's say you have, as Amindan had mentioned an example, let's say you have something like 10K samples, and what we can do is we can divide this into, let's say, 10 batches, and every batch gets 1000 samples, and we can use these 1000 samples to update our weight vectors. So for every epoch, every one iteration, we are going to update our weight vectors 10 times.
I have one question in the comparison.
Sure.
See, the weights learned by mini batch approach and normal approach, will it be always exactly same irrespective of how I'm batching, or the batching has to be like, we have to follow some strategy to batch them?
So your question is, let's say if I train my model with mini batch is equal to, let's say, number of batches equal to 10, and in another run, I train my model with number of batches is equal to 20. Are they
let's compare between the normal, which I'm taking all the examples, and the one mini batch. These two. So can I expect the same at the end of training? Expect the same weight? Both are giving me the same learned weights.
Well, if you ask me, see, mini batch gradient descent was designed to make progress quickly, and save some computations. So it will move very, very close to the optimal solution, but I cannot say that, after running so many number of iterations, you will definitely reach to the same solution as the original gradient descent. But yes, theoretically, if you give that, infinite amount of computation, it should. Given that we are also changing our learning rate, adjusting it, yeah, it's possible. Any more question?
No, also the follow up on that. Also, let's say mine is not a linear data. It is, for example, let's say polynomial itself. Now my batching depends, right? How it is. What I'm training with in my first iteration, what I'm training the next iteration. Let's say my data is on the one piecewise, basically. So one could be a kind of a normal quadratic with a negative sign kind of a data, and next batch could be the opposite.
Okay.
So how will not that play a role in how we batch them actually?
So good point. See, both of them are actually part of your data. So definitely they should influence your model. The only point I would say is in the individual weight upgrade sessions, these two might produce opposite results. That is possible. Yeah. And sometimes what happens is mini batch, and this is the case with the stochastic also, they move away from the optimal solution, or some direction which is not directly pointing towards the optima. That is possible. But again, what we are trying to do is if you move over the entire training data in batches, you are definitely making more progress than the standard gradient descent.
No, my question was that should it be a strategy in batching them, or should it be like free? You are free to pick.
Well, you are free to pick the larger the size of your set. I mean the batch. The more it is going to be closer to behaving like a standard.
Then that itself will become a parameter to decide what is the right size.
Yeah, you can think of it. But then W will also become your parameter, right? W and batch size. Where you start and what is the size of the batch on which you train it. So yeah, if you can afford it, I mean the problem is such that you can take larger batches. That is fine. The larger the batches, the closer it is going to be pointing towards the optimal minima.
Okay.
So
yes,
in a crude sense, mini batch is also having the same way of computing than like gradient descent, the batch size gradient descent, right?
Yes.
In just the differences of the size of the sample, right?
Exactly.
Okay. Okay.
Okay. Now comes the very popular stochastic gradient descent. So stochastic gradient descent is a special variation of mini batch where the batch size is 1. That means every batch has only single sample. So if there are n number of samples in the data set, there are n number of batches for stochastic gradient descent. Now this is even extreme version of your mini batch gradient descent in which the batch size is 1. It cannot be smaller than that. So in stochastic gradient descent, after reading every sample, we update our weight vector. Okay, so now let's go ahead and see that. Okay, maybe yeah. So there was an animation in the slides. So let's move forward and look at this and compare the trajectories taken by the three variations of gradient descent.
Sir,
yes.
If you don't mind, can you also go through the codes of these three? I mean, GD, MBGD, and SGD, if you don't mind. Just once go through of it.
Okay. Can I do this at the end of it? Because we have.
Yeah, but it would be
also.
very helpful if you just explain. I think some people might have the problem. Even I don't. I also have some doubts in it. So if you can.
Sure, I'll do that. But is it okay if I do it at the end?
Yeah, but please do it. That's
sure. Yeah. So in this, diagram, the trajectories taken by the three variations of gradient descent over the loss function, it is very, very clear. The smoothest one is the blue one, which represents the standard gradient descent approach, in which we go through entire training set before updating our weight vector even once. The the green one is the mini batch. You will see that it is taking an erratic approach. It sometimes moves away from the optimal solution, but slowly it is getting closer to the optimal solution. And when it gets to the optimal solution, there are a lot of iterations which are, just hovering around the optimal solution. On the other hand, stochastic gradient descent, you can see that it is making even more fluctuations before it reaches the optimal solution. It is expected because the individual data points or individual samples might force it to move in a direction which is not pointing towards the optimal solution. Okay, now these are the learning curves of gradient descent, mini batch gradient descent, and gradient descent. As expected, the batch gradient descent is the smoothest. It is monotonically decreasing. Mini batch gradient descent, the number of you can see that it is fluctuating, but the highest number of highest amount of fluctuations you will see in stochastic gradient descent learning curve.
So in this, the iterations for SGD is the number of epochs or number of steps?
Pardon me, can you please repeat that?
This number iteration, the x-axis for
yes.
SGD is the number of epochs.
Yes. They should be number of epochs. Or good question, sir.
Actually, it should be whatever step at which you compute that respective update.
So then the number of epochs may be
in
much
the case
smaller.
of batch GD, it would be the proper epoch in the real sense. In mini batch GD, it will be n by k. Whereas in stochastic, it would be a single sample. We could still plot them like this, but I think if we were to, the x-axis was the actual update step, whatever that is, that would be like a more realistic comparison, I guess.
Okay, I think it should be epoch, if I think right now, but I'll let me look at the code also, which I'll be showing after some time, and I'll confirm this, sir.
Because if it is actually epoch, then they should all look the same, right? I mean, at least similar, more or less.
Yeah, but in the code
Not
also, if you see
identical.
the mini batch, they are using high percentage stain or something, and after that they are updating the weight. And that weight only, because after calculating the weight, we are plotting this chart. So we are calculating all the weight by the epoch.
Yeah.
And then we are updating. That's why stochastic is showing a up and down more compared to your batch gradient or not.
That was the doubt I had, because in codes we have used number of epochs and here we are using iterators. I'm a bit confused in that.
No. This iteration means when what Jadhav told, when you are calculating, updating your weight in the error, the loss, where you are putting it.
Okay. Let's visit the code, and I'll definitely clear this one. Okay, now once we have done the optimization, we want to figure out how our model is doing on unseen data, and for that we do root mean squared error. There are multiple matrix which can be used: mean squared error, mean absolute error, sum of squared error. Now this is the recap of the entire linear regression week, which is week 2. What is the data? How your model looks like? What is the loss function? The 2 possible optimization procedures, and your evaluation metric. And in the next slide, all these things, the details are also there. For example, data, it is actually a tuple of feature matrix and labels. How does the linear regression model look like? Y is equal to xw. The loss function, its equation, the optimization procedure, no change over there. And the evaluation we are doing with RMSE. Okay, so if there are no further questions, I can move forward to week 3 with polynomial regression.
Yes, sir.
Okay. So Now this linear regression part is done. That means we can train a linear regression. We can conceptualize a linear regression model. We can fit it either with normal equation method or gradient descent, any variation of gradient descent, evaluate it also. So we are now we have a full grasp of one machine learning model, which is a linear regression model. Now let's come to the point where the data has relationship which is not linear between its features and its labels. Okay, so something like this. Now what we want to do is we want to capture this relation. If we go with everything that we know so far, which is up to linear regression, then your HWX, which is the red curve, and your blue dots or blue circles are the data points. The green curve, which is sine 2 pi x, is your generating function. Then you can find out that your model, the red curve, is not doing a great justice for fitting this data. So what is happening is it is not capable to fit this kind of complex data. And how can we fit? Now this entire week was about that. For this kind of situation, we want polynomial regression, and that what that means is it is basically linear regression, but before we apply linear regression, we transform our features polynomially. This is our sample data. This is what our model looks like. It is not doing a good job. It is actually underfitting. This is your training and validation loss curves look like. Your validation loss is small. Maybe some point we chose for validation set turn out to be on the this linear model. The training loss, it is not great. It is poor. It should be lower. So now how can we remove this underfitting problem? So one thing is by increasing the capacity of the model, and we do that by applying polynomial transformation to our features. And this is how it looks like. So if we apply a polynomial transformation to our feature matrix, then the size of the weight vector also changes. This is something important. So here are some examples of polynomial transformation. The second one is a polynomial transformation on two features x1 and x2 of degree 2. The third one is polynomial transformation of x1 and x2, two features of degree 3. And you will find that on the right hand side for degree 3, these are the so first two, which are these two, x1 and x2, they are the original features, and everything else which is written right after that, they are generated features. So this is the code for generating polynomial transformation. I think we have gone through this one in quite detail in Solve with Instructor.
Yeah, this is clear.
Yeah. Some examples of polynomial transformation. Now let's fit polynomial model of different orders on this data. Okay, now it is more interesting because by changing the degree of our model, we can see that we are getting better results, possibly better results. So the first one, m is equal to 0, m represents the degree. It is the first model, not the first model, sorry. It is going to be a straight line. M is equal to 1 is the model that we fit for the first time in early slides. M is equal to 3. Now it is looking better. It is going. It is trying to at least go towards very close to the generating function. M is equal to 5. It is doing even better job than m is equal to 3. M is equal to 7. Okay, now it is definitely going through all the points, and at the same time it has started to fluctuate more. And with degree m is equal to 9, you can see that it is a zigzag function. It is going through every point in the data set. and possibly missing the pattern which is there. So this leads to the next problem. Even though now we are able to create more powerful models, the problem is there. If we started to remember the data points, they're going through each and every data point, and which is leading to overfitting or poor generalization. And this is what actually proves our point. So blue curve is the training curve, and the red one is the validation curve. You can see that as the number of degree increases, the training error is actually continuously decreasing, but the validation error is increasing. That means our model is not generalizing well. Now comes the point. Now we know this problem. How do we solve this issue? Okay, so before we go into solving this issue, first we want to observe what is happening to our model when our model is overfitting the data. And you can observe that these vectors, the parameters of the weight vector, they are getting increasingly large in magnitude. So this one is close to 30,000, this is over 50,000, 52,000, and so on. So these large weights actually cause the problem of these fluctuations. So now we know what the root cause is for our overfitting. Now, how can we address the overfitting? There are two ways to do this. One is use larger training sets. The other one is use regularization. So, for example, if we increase the size of training set, we go from a model which is on the left hand side to a model which is on the right hand side. You can see the right hand side model is more representative of the pattern in the data. The reason for that is if there are many number of points. So see, degree is 9 and the number of points is 15, right? So there's not a huge difference between those two. But on the right hand side, what you will see is the degree is 9, but the data points are 100. So 9-degree polynomial cannot overfit such a large data. Okay, so that's why we are going to see a smoother curve on the right hand side. The other way of avoiding overfitting is using regularization. By regularization, what we want to do is we want to force our training procedure, which is our optimization procedure, to not allow these individual parameters of the weight vector to increase to very large values, increase in magnitude. So either they could be large negative numbers or large positive numbers. And this is what we want to avoid. So what we do is, in our loss function, we add this penalty term, which is going to be some function of our weight vector. Lambda is actually our regularization rate. How strongly we want our weight vector to, individual parameters of the weight vector to increase or decrease. Sorry, how much do you want to suppress that? And that is going to be controlled by lambda. Now, there are only two types of regularization that we have discussed in this week, which is L1 regularization and L2 regularization. L1 is lasso regression and L2 is ridge regression. Combination of these two is also possible, which is called elastic net. This is how your ridge regularization equation for loss function looks like. Now we can actually compute its derivative. This is what it look like. Now, after doing this, we can either use the normal equation, and this is how it will look like with your regularization rate. Okay, and there are two important points at the bottom of the slide. One is what happens if lambda is 0. Then you get the equation which we previously derived in week 2. And what happens if lambda is infinite? That is, you will see that since we are taking inverse of this particular matrix, if the that matrix has very large values, and since we are taking inverse, we are going to get weight vector which is going to be close to 0 or 0 itself. In other words, if there is no regularization, there is no penalty basically. So we are going to get the same expression. If there is huge amount of penalty, that means we are suppressing our weight vector too much. It is not. It doesn't have any wiggle room, and therefore we are going to get a weight vector which is close to 0. The next method to get the optimal solution with regularization is gradient descent update rule. Now we have calculated what our derivative is with respect to weight vector. We can use that here and multiply it by alpha as we did earlier, and this is what we get to update our weight vector. Okay, there must be an animation inside this slide deck, but now we don't have it. Effect of regularization you will see is as we increase the value of lambda, the model moves away from overfitting, and if we increase the lambda too much, then it goes towards underfitting. Something in between is we want to find out. That is the sweet spot. What value of lambda where our model fits the data very well. So this is the next important point that has to be addressed. How do we choose the best lambda? So in order to choose the best regularization rate, we have to experiment with multiple values of lambda. And for every value of lambda, what we do is we fit our model and calculate the error on the validation set. We do this for all possible values of lambda we are considering. We draw a chart, and on the value for which we get the lowest cross-validation error is the lambda value we choose. That is the optimal one. Now we come to lasso regression. So lasso regression, since the function is not differentiable, we have to use some other methods other than gradient descent to optimize it, which is out of the scope of this course. So if, in ML practices course, we are going to use lasso quite easily because those optimization procedures are already implemented in scikit-learn. We can take advantage of that.
So should we expect questions on lasso in our exams or anywhere?
Well, only up to the details which are covered in slides as well as lectures. That's it. You will not be asked any question on how to optimize a lasso regression model.
Okay.
All right. If there are no further questions, Nitin can take over.
So just one question I
Sure.
had, like if we have
Sure.
to decide underfitting and overfitting by visual inspection, how, I mean, I think there was one graded question where there was a bit of confusion. So can we just take that example and see how to do it? Because in the slide example, there was not much noise, but I think it was there in the question. So.
Okay, so is it in the mock quiz or somewhere
No,
else?
it's the graded in week 3 graded assignment.
Okay, give me one moment.
Yeah.
Okay, is my screen visible?
Yes, sir.
So mock 3 graded assignment.
The GA3.
This is program.
Objective type, yeah.
It is below
that.
Last one.
Okay. Which question is that?
This one, the third one. Yeah.
This one?
Yeah.
Okay. So which of the following is our true statements? Okay. Model with m is equal to 1 underfits the data. Okay. So the blue points are data points. Okay. And the red line is our model. So this one has to be true. Okay. I cannot select it anymore. So M1 definitely underfits the data.
Yeah. Yeah.
M is equal to 1 smoothly fits the data. Definitely not true. For degree is equal to 1 is equal to 1, it becomes y is equal to mx plus c, which is a straight line, and definitely it is not going to work. Model M is equal to 3.
So
Okay.
3 and 7 is where I was a little confused. Like, how do we know if 3 is underfitting or?
Okay. Okay. So your, I would say 3. Right.
Actually, Amruta ma'am has mentioned on discourse that there was some problem in the question, and the correct answer is the answer that is marked correct is not actually correct.
Okay,
But,
so I
yeah,
wasn't sure what was the correct
reasoning
answer.
Behind, say, m equal to 3 fitting properly and 7 not fitting properly, or other way around, whatever it is.
Yeah.
And basically, we can only comment about m equal to 1 and 12
right.
With precision.
Right. For m is equal to 1 and 12, the difference is like day and night. We can say that.
Yeah.
For 3 and 7, yes, I see your point. 7 could also possibly be a good model.
But so we could say
given
that it's underfitting. It's either underfitting or smooth, maybe not overfitting. But then until you have that train and validation split, you can't tell for sure, right?
Yeah,
it could be a smooth fit also, because it seems it's covering most of the data points.
But against the number of data points we have, isn't it overfitting?
Yes. Yeah, that's the right point. If it is covering all the data points, it may be overfitting.
But it is not. No, that is the thing, right? It's going through some and.
But in the answer, people lost marks because people had marked M7 as overfitting. So now in the discourse, it is corrected, it seems. So you need to go back.
In the discourse, it is underfitted, right? It's overfitted, right?
Yes. I know. I have not seen the thread. So Jaidev is mentioning it.
So, but sir, according to you, what will it be? Is it overfitting, smooth fit, or underfit?
So I think the option 3 seems okay. That seems smoothly fitting. 7, it's borderline. I mean, if this would have been a real world problem, I would have asked for more data.
Honestly, I have decided like a simple algorithm that if there are too many curves, it's overfitting. I don't know why, but all the questions.
Nothing but higher degree.
Yeah, nothing but higher degree. It's overfitting.
Oh no, it's not like that.
I know, but most of the questions are answered in the same way.
Visually, it is impractical to give such a call, actually.
Yeah, so visually we can only do for data sets with few number of features only, 1 or 2. This is one. This is one feature data.
Okay.
The real question is, should we expect something like this in the quiz?
that was my main concern actually.
It's very obvious that something like this will be asked the day after. Like they will, because this is a very confusing question. Even on the day of submission, it was very confusing, like how to do it.
So, this kind of questions we can definitely ask for one feature data. But your point is right. They should be distinguishable enough. The options should be like that.
Or at least they can provide the learning curve with them. So much more.
Yeah. If the learning curve is there, you don't have to look at this at all.
It shouldn't be debatable.
Yes.
What the correct answer is.
Yes.
Maybe the answer could be framed such a way. Possible, maybe, kind of. It cannot be definite. You can add a maybe in the sentence.
Well, M is equal to 7. It looks like at some places it is, it is bending too much.
Yeah,
But again,
so
yeah.
overfitting, yeah.
Okay.
Sure, thank you. So just one other
Sure.
question.
Sure.
What could a situation where validation loss is less than the training loss mean?
Validation loss is less than the training loss. It is a, so I think I see your point. In some of the slides we saw that, right?
Yeah, it actually happened when I did the code also. So I think the reason it could also be fewer number of training test samples.
See, what I mean by happening, so your data set was small, I take it. Right. So this is only possible if your data set is small, and I mean randomly the test or validation set was chosen, something like that. It was very close to the model, even though the model was underfitting. So high value of training error means it is definitely underfitting.
Okay.
Yes.
Okay, but because I think what happened in my case was the model fit both of them, but the test set samples were fewer than the training set.
That is right. That is, I mean, test set are going to be fewer. Whenever you do this, ask this kind of question. If you want to derive very definite conclusion about whether our model is overfitting or underfitting, your training or validation set on which you are, let's say, talk about only validation set round. So your validation set must be good representative of your training set.
Okay.
Right. For example, let's say, give me one moment. I'll draw something, and maybe that should give better example.
Basically, they should be both coming from same distribution.
Yeah. In other words, that is absolutely right. So even coming from same distribution is that is theoretically very, very true. For that, we have to make sure that our data is large. So something like this. See, in the example that we saw, okay, so the example that we saw was something like, so we have these data points. So why I'm taking this example? Maybe I should just copy paste from there. Okay, so this is our data set.
Yeah.
And just it happens that your validation set turns out to be these two points, or the point which is this one also possibly, or this one, which are closer to your model. In situations like this, you will have higher training loss and lower validation loss.
Okay, but understood. But then does that necessarily mean that it is an underfitting model? And that's why it is showing higher training loss? Because in my example, I use that sign generating function for both. So when the number of test samples exceeded a certain number, right, then it became the same. But test samples were fewer. That is when it showed like validation loss is lower than training loss. So my question is, that situation, does that necessarily mean the data is underfitting, or it could mean something else?
Okay, so for underfitting, okay. So we have two situations. One situation, so let's say this one is our training loss. This one is our validation loss.
Yeah.
Something like that, right?
Yeah.
So this is situation number one. The situation number two could be both of them are high. So this is your training one, and this is also your validation one.
Yeah.
So you're asking whether the first one points to a specific case or not.
Does it always mean underfitting only, or could it mean something else?
Training error is high. Validation loss is low due to some unfortunate randomization. I think no, it cannot mean anything else but underfitting.
Okay, sure. I can also share the code on discourse, maybe. Just raising this question, like what I wrote and what is giving me this error.
Okay, sure.
Yeah, thank you.
So yeah, so as you also mentioned that as you increase the size of your validation set, the situation was more like this one.
Yeah.
Yes.
Yeah.
Yeah. So that is more. That is a better and more, I would say, firm representation of what is happening in your training.
Okay. Okay.
Yeah.
Sure. Thanks.
Nitin?
Sir, can we take the last question of the mock quiz? If you have opened that before, or can we do it after week 4? That is also okay.
Let's see. Okay. Yeah, let's look at that after week 4.
Yeah, that's fine, no issue.
Yes, Anil, thank you. Good evening,
yeah,
everyone.
sorry, Nitin, sorry about that. We are almost at the end of this session, and now week 4 stance is coming. I hope everybody is okay with that.
Yeah, that's fine.
Okay. Thank you.
Okay, so let me share my screen first. Okay, so till now we have done modeling or techniques for regression problem. Now in week 4 we will see some techniques or some models for classification problems. And as of now, you already know the difference between regression and classification and the basic terminology. So for now, I'm gonna skip this part. Only remember this: in classification problem, the only difference from the regression problem is that here in the output label or the label is your belongs to some discrete classes, not a real number anymore. So this in this week 4 we have seen two approaches, or say 2 techniques for the classification problem, and these belongs to linear model. Okay, and what I mean by linear model is that so first understand what actually our data is. So if there are m features and there are k classes, so my input feature or input space will be a m dimensional space. Let's say if there are 2 features, x1 and x2, so your input space will be, your data will be distributed into 2-dimensional space. And what our task is, and let's say there are 2 classes, binary classification problem. So what class 0 and class 1. Now we have to distribute the data set into 2 classes, 0 and 1. So our data set, let's move quickly to understand the data. So something like that. Your input space will be 2-dimensional space, and our task is to divide this input space into 2 different regions, such that each region corresponds to 1 class. In case if there are 2 classes and there are 2 features, your input space will be 2-dimensional space. Our task is to find such such a separating hyperplane, or say decision surface, so that it can divide the input space into 2 regions, in which one region corresponds to class 1 and one region corresponds to class 0. So how to do that? And by in this week 4 we will do the linear model for the classification. And what I mean by the linear model is that the decision surface or the separating hyperplane that we are going to learn is the linear combinations of features. Okay, in this case, if there are 2 features, then it is going to be a linear combination of x1 and x2. Okay, so this is how your actual problems look like. So here in week 4 we have 2 model. One is least square model, second is Perceptron model. So let's quickly move to the discriminant models, discriminant functions. So discriminant function is the function that takes the input and associate and maps it to the actual outputs. And how to learn this model. Okay, so this is your linear by equal to w W naught plus W transpose X. So this is your discriminant model. And remember that if there are m features, your discriminant functions is discriminant function gonna be linear. If the discriminant function is linear, then your the decision surface is gonna be hyperplane or hyperplane in n-1 dimensional space. So remember here there are two features. Then your decision surface or the hypersurface is gonna be a line, and line is one-dimensional space. If there are only one features, then what actually this discriminant function will look like? It's just a point. And remember, point has no dimension. So if there are m features, your decision surface is gonna be a m-1 hyperplane. Okay, so this is something data will look like. So let's move to the model quickly. So this is your models look like. Discriminant model. So if W naught plus W transpose X greater than 0, then you will classify that that example to be class 1, and if it is less than 0, then you will classify that example to from class 0. Okay, so this is this is a model for the discriminant function. So main thing here, what actually these W and W0 represent in our discriminant functions. So for that we have derived this thing. We have taken 2 points in the decision surface and we have subtracted them. Then if you look at this this particular expression, W transpose times XA minus XB equal to 0. So it says that W transpose is actually orthogonal to this vector XA minus XB. And remember, XA minus XB is the vector lying inside the decision surface, because XA and XB we have chosen in the decision surface itself. So it means that W vector is the orthogonal to the hyperplane that we are gonna learn, right? So W represent the W actually gives you the orientation of that hyperplane. And for W naught, what W naught represents? So we have chosen a point from the decision surface. From there, we have come to this expressions. From there, we can see that W naught is nothing but the normal distance from the origin to that hyperplane. So actually, W vector represents the orientation, and W naught that bias we call, it represents the normal distance of the hyperplane from that origin. Okay. So let's say for this this particular setup, this is your hyperplane, that is a line. So W naught actually represents your orientation of this line, and W naught is gonna be the normal distance from the origin up to that hyperplane. And for a particular example, let's say for such any x, if you find the value of W naught plus W naught plus W transpose X, then that by actually represent the sign distance of that point from the hyperplane. Let's say this is point here, so by will be a sign distance. Sign means either up positive side or negative side. Okay, so distance actually by denotes your distance of that point from that hyperplane, hypersurface. Okay. So any problem up to this point? So remember, W naught determines the location because it gives you the distance from the origin, and W, the vector W, it determines the orientation of the decision surface. Okay. So your data are distributed in m-dimensional space, and your hyperplane will be m-1 into the m-1 hyperplane. Okay. So this is this setup we have done only for 2 classes, where we have only class 0 and class 1. But for multiple class, there may be 2 ways for this classification problem. One is 1 versus rest, and another is 1 versus 1. So 1 versus rest, what we will do, we'll choose for class K. Let's say CK versus not CK. Such K minus 1 discriminant functions we learned. Okay, so let's say there are K classes, then for ith class we learn Ci versus not Ci. For such K minus 1 discriminant classes we learn, and for 1 versus 1 classification problem, what we do, we choose we takes the pair, all possible pairs, and learn the corresponding discriminant functions for that. But there is some this ambiguous region we can have in such approaches. That's why we don't go for such 2 approaches. So let's look at what those problems with these 2 approaches. So for in 1 versus rest, let's say there are three regions, three classes. For that, we are learning. There are three classes: class 1, 2, and 3, and we are learning discriminant function C1 and so we are learning discriminant functions for class C1 and C2. So it will look like C1 not C1, C2 not C2. So look at this this particular line. This is discriminant function corresponding to class C1. So it is, this region is C1, and this particular region, this entire region is not C1. And this discriminant function is for class C2. So this particular region is gonna be C2, and this is not C2. Now look at this region. This green region. So for this discriminant function, it is C1, right? And for this discriminant function that we have learned for C2, it is C2. So this is ambiguous. It is again C1 and C2. So this kind of region can be ambiguous in the case of
not sure others are able to hear. It's a lot of noise system.
Sorry.
Your audio has some problem. I think I don't know whether everybody is having the same problem.
Is it with everyone?
Yes, so it's not very clear.
And also, please, can you go a little slower? I think we are going too fast.
Just give me a minute.
Yeah.
The problem with my earphones. So let me change that. Is it better now? Hello, am I audible?
No, you're not. Still
Not
the
very
same.
much.
Yeah, I think you have the mic is far away or something.
Hello.
Yes, then you're audible.
So is it better or not?
Yeah, now it's better, I think.
So someone mentioned I'm going a little faster.
Yeah, maybe a little slower you can go. Because too much scrolling and we are losing track.
Okay, so whatever we have covered till now is just the about the training data set. That's why I skip all those slides.
Okay.
Up to there, all those slides is about the data set, and we already seen how does the data set actually looks like in the regression problem. Here it's only that your label is discrete classes rather than the real numbers. Okay. So so up to this point is clear, or anyone has doubt? Okay, not so this is the issue with one versus rest classification problem. And if we go with one versus one, that is, we choose every pair and we try to learn discriminant functions for all such pairs. Let's say there again the same problem. There are three classes 1, 2, and 3, and for class 1 and 2 we will learn the discriminant function, that is this discriminant function. So this will be C1, this region will be C2 for this discriminant function. For this discriminant function, this is for C2 versus C3. So this region corresponds to C2. This entire region will be C3. Similarly, for this line, this is for C1 versus C3. So this region corresponds to C1 and this region corresponds to C3. So if you look at this region, this is gonna be your C1. For this discriminant function, it is gonna be C1, and for this discriminant function, it is gonna be C2. Right, so it is kind of ambiguous region. We are not sure which class it actually represents. Okay, so this is the issues with these two approaches, one versus one and one versus rest classification problem. So how to fix it for this? Rather than going for 1 versus 1 and 1 versus rest, what we do, we just take linear combinations of key linear combinations, and we learn simultaneously all such discriminant classes at the same time. So it actually concretely, if you see, it looks like something like that. If there are key classes and features, so we will learn these models at the same time. And for a particular example, if by I is the highest value, then we will say that that example belongs to class I. Okay. So we assign by k to example x if by k is greater than by I. That means that example x belongs to class k. And for any two decision surface between two classes, it is just the same as for, let's say, we are to find the discriminant decision surface for class by class I and j, then it is same as by I equal to by j, and by I equal to by j will give you the form something like that. For binary classification, it's the same that we have seen in this earlier case. And remember, whenever you are doing classification problem using least square classification, you have to convert your label vector by the one-hot encoding scheme. Okay, so in this week we will learn two ways. One is least square model, second is perceptron. So let's move to the least square, then we will go for the perceptron. So least square, here the loss function is defined as, so all these slides you can go for. So error is defined as actual label and predicted label. Predicted, you already know, this is the linear combination of the features, and this is the actual label. So this is how you define the error. And remember this, now this is the embedded encoded label vectors, not that just a class. Okay, so this is your error, and total error is defined as sum of all such errors for all such data points. And back in the vector form, you can write it as it is just E transpose E, where E is error. So let me see, where is the vector form here.
Sir, can you go on the code once again of the above? Yeah.
This code?
Yeah. So here we are just converting if I mean into an array, right?
Yeah, this is for training data set. So we will calculate value of xw. Remember from the regression problem, you have calculated by equal to xw, right? So whichever is greater, we will if it is greater than for 1, then we will classify as class 1, and if it is greater than for class 0, similarly like that. Just whatever we have seen here. Yeah. So here, if it is greater for the classes, if by k is greater than by j, then we will classify that x for by k. If it is greater than for all such I and j and k, right? So we just calculate these values, and for what index it is coming larger, we will classify that example to that class. Okay.
See, here we can use np.where also, right?
Yes, we can.
Instead of doing loop comprehension, can we just do np.where?
Yes. Yeah.
Where then, if you use np.where, then you have to look at the actual value of that xw, right?
No, here in np.where z-val, this z, okay, z greater than 0, then comma 1 comma 0.
Yeah, that you can do. np.where 1 np.where xw greater than 0, then you can write 1, otherwise 0.
Correct. Exactly, it gives the same thing actually.
Same thing, yeah, it will give the same.
Can you go to that loss one? Because loss, it is exactly your regression loss. Okay. Here we have not. Go up. Scroll up. Yes. Hold on. Now here, like, we have not taken half. half as a constant, right? But in the collab, when we did this, that time that half is included.
Yeah, if you remember from the collab, that by there is remember that by is encoded label vector, right? Every time, and
Yes.
1 by 2, then trace of that matrix. If you remember, if you do x into w, then that gonna be your matrix. And loss function is always a scalar function. Then you have to calculate this trace of that matrix. The trace itself will give you the loss function.
No. Here your xw minus y. It is a, say for example, it is not a a multi-level. Okay, your y is a single component.
Oh, yeah.
In that case,
again you have to do encoding for that by, and that region for 1 by 2 is just for mathematical convenient, because
right.
in gradient descent you just find the derivative of 2, so 2 comes out and just cancel out. Just for mathematical convention we use 1 by 2 in the loss function.
Correct. Now the question is, in this expression, right, since that half has not been taken, whenever you will take the derivative, you will get a 2, right? Yeah. In the collab, the half was taken and the 2 is not there, right? Now say for example, if you ask a question in the exam, that okay, calculate the loss function. Do I use that half or not? If I don't use that half, then I will get an answer. And if I use that half, I will get a different answer.
Okay.
Yeah.
So your doubt is
so even in mini batch and stochastic, there's a 2 which is coming in because half is not used, I think, in the code for mini batch and SGD.
No, in the code for the classification problem, if I remember correctly, so we have used 1 by 2 for the loss function, right?
No, I'm talking about week 2 regression, where the mini batch and stochastic is implemented. There's a 2 into the gradient, which is calculated.
Okay.
So again, same question. So is should we use half or not consistently?
Yeah, for just for the quiz, we know why that half is required.
It's better to use half throughout all in regression and classification problem.
Okay.
So if in particular quiz, if there are any such questions, then you can use half there.
Okay, sir. Thanks.
Okay, sir. Thank you.
I think that the importance of half was covered in MLF towards the end. I think it gets cancelled out somewhere.
So the importance of half is only for the mathematical convention. Just I just mentioned because we take the derivative for calculating the gradient in the normal equations. Whenever you're finding the minima using normal equation, then it's not a problem. If you use any constant before that, it's not a problem, because you just set up the derivative equal to 0, so the constant goes vanish, right? But in the case of gradient descent, you just update your weight vectors using the derivative there. So there half comes into the picture. So just to remove those half, you just if you take the derivative to comes before the expression, the square terms comes out. To remove this, we take half in the loss function just for the mathematical convention. Okay. Is there any? There is no any theoretical importance for that. So here I was looking for that expression. I think it is not in the slides. So JW will be something XW minus Y transpose XW minus Y and trace of that expression, right? And you can take half outside that. So the JW will look like half and trace of XW minus Y transpose XW minus Y. So this is how your JW will look like. And so this is your loss function. So now this is the similar kind of thing that we have done for the regression problem. There are two approaches to find the minimum for such loss function. One is optimization, where we take the derivative of the loss function with respect to W and set equal to 0. And if you do, then W will come out to be X transpose X inverse X transpose Y. Okay, so here X need not to be full rank always. That is, X need not to be invertible all the time. That's why in the coding, whenever you do, you just calculate the pseudo inverse of x transpose x rather than the inverse of x. If x is, if you remember this expression, I think someone has asked before as well. If you remember x transpose x inverse, if it is x is always, if you are sure that x is invertible matrix, then you can write it as x inverse x transpose inverse, right? Open that. Remember, a b inverse is equal to b inverse a inverse if the a and b both are invertible matrices. But in our case, in real world data set, x need not to be invertible all the time. Remember, there can be examples which have the same features values, or there can be features that can be dependent as well, right? So x need not to be full rank all the time. That's why we just keep this in this form. Not we just don't calculate the inverse of x transpose x. Okay. So this is your W using your normalization. Second approach is finding using iterations that GD and gradient descent. So the same approaches we update our weight vectors every iterations. Let's say for I iteration, you have weight vectors W0, W1, W3, and gradient descent. What you will do, you just calculate the derivative and just take the difference from those weights. So this is how you calculate your weight vectors in normal equations and optimization using iteration problem. I mean the gradient descent problem. So I think some part is missing in the slides. I didn't take a look at this. So these are the slides that I have taken from the portal. Okay, so you can use those slides to study.
I think we are missing the perceptron, the whole perceptron class.
The perceptron slides are with me, but I think we are missing that SGD stochastic gradient descent part here.
Yes, you are missing that. Yeah.
So any problem in this approach, in this model? So only need to remember, you have to remember model and what is the loss function, then how to optimize that loss function, right? So next approach is Perceptron. So this approach is rather easy than that. We will come to this mathematical part later. Then just look at that example that I have taken. How actually they are updating our weights. Remember this. So this is your decision surface. So in the Perceptron, what we do is we will just randomly initialize your weight vectors, and the model is same. Here we take the linear combinations of the features and we apply the n activation function to that. That is, if the linear combination is greater than 0, then we will call it from the class 1, and if the linear combination of that example is less than or equal to 0, then we will call it to the minus 1 class. Okay, so we randomly so in the Perceptron algorithm, what we do, we randomly initialize your weight vectors, and let's say at this particular time your decision surface looks like that, and if you remember this red point, it misclassifies. So what we will do, remember W denotes your orientations of the hyperplane. So we will just change our weight vectors for that misclassified point. So we will add the x to that W vector. So what does happen? The direction of weight vector changes. So the directions orientation of the decision surface changes in a way that misclassified point tries to come into the correctly classified region. Okay, so actually in Perceptron algorithm, we are changing the weight vectors only for those classes, those points which are misclassified in a way that that classes tries to come in the correctly classes region. Okay, so look at from the starting what actually happening here. So one thing about Perceptron is that Perceptron is only applicable for binary classification problem. And here we have removes our classes with +1 and -1, and the data should be linearly separable. Otherwise, the Perceptron algorithm will never converge. Okay, so these are two important points for the Perceptron classification problem. Yeah, what we do is just this is how your model look like. This is your phi denotes the feature transformation, that is polynomial transformation phi of x, and w is the weight vector. So we take the linear combinations of that transport features, and then we apply the nonlinear activation function to that. And in this case, our nonlinear activation function is just the step function or the signal function. If the linear combination is greater than 0, then we will call it from the class 1, and if it is linear combination is negative, then we'll call that example to the class negative. So our activation function is signal function in our case. Okay, so this is how your model look like. So this is the picture, and this is the plot for signal function. If the input is positive, it takes the class 1, and if the input is negative, it takes the class it is the value of function is -1. Okay. So and the perceptron loss function looks like, so prediction but error is defined as if it is classified correctly, then we call the errors to be 0, and if it is misclassified, that is the by I is not equal to by I hat, that is predicted is not equal to the actual level, then we classify it as to be the linear combination times by I. And now look at this function, this is actually +1 or -1, it is actually +1. So this function you can write it in this one, maximum of 0 minus 0 of 0 and minus the model and by I. So look how this actually gives you the error of 1 if it is misclassified. So look at this. If the decision is wrong, that actually it is -1 and it is classified +1. That is misclassified point. Then in this case, your SW stick value is +1 and by I is actually -1. So minus is already there. So maximum will be 1. So in this case, the error is 1. Again, if it is actually positively, the actual class is positive and it is classified as minus class, then your error is again gonna be -1, and it is classified correctly, then it is +1. Then remember this term is gonna be negative, so maximum will be 0, so error will be 0. Again, if both are negative, that is if the predicted and actual classes are negative, then this particular term SW on by this particular term is gonna be negative, so maximum of 0, maximum gonna be 0, and so again error is 0. So this expression, remember this expression for the error for the perceptron classification problem. This to that.
Sir, your HWXI is basically the sine function, right?
Sine function, yes, that's signal function. Yeah. So if you see that loss function is nothing but the number of misclassified points, right? Because every time if it is misclassified, it adds to 1, and if it is classified correctly, then it adds up nothing. So it actually loss function is nothing but the number of misclassified points.
I think we are not able to hear him, right?
Yes, he's not audible.
Nitin, you are not audible.
Nitin, maybe the mic is far away. Can you please readjust it? Very faint volume is there.
Nitin, can you hear us?
Yeah, I can hear you. Hello.
You are not audible.
Hello. not audible?
No, Nitin, still very, very faint volume. Not audible.
So maybe we can move to that mock question, last question, till he.
Okay, Nitin, can I suggest to remove the headphone jack and plugging it back?
I did that, but it's not working.
I see. Can you keep the mic closer? Closer. Can you try that?
Hello.
Yes. Yes.
So in the interest of time, at least we can cover the 2 questions I have. Probably, I think we need to prepare for the exam. So that's fine. I think we understand most of the concepts. I have a doubt in 2 questions, and then probably.
So is that okay with everyone that we cover more questions right away?
Yes, yes.
Hey, Anush.
Okay.
Apple முடிக்கணும்டா. Sorry about that.
Hello.
Yes. So yeah, this question shows multi-class, multi-label, but it is binary label, right?
Can I explain this? Try explain this.
Yes, please, sir.
Simple, right? See, look at the difference between class A and B, right? A, each row has only one. That is exactly 1. Everything else is 0, right? In section B, each row there is more than one, right? So
do we not look at the feature value? We just need to look for the label, is it?
Yes.
Only that, because see, classification is about on the labels, right? The features can be anything, anywhere, right? That doesn't change the classification at all.
But do we have
Only
some
the label
relation between feature and labels, right? On what basis they have labeled it?
No.
We don't need to think.
Yeah, the way, let me complete that. So the way I understand, you need to look at only the label matrix. I don't know why they have given the feature matrix. That is just extra information in this particular case, at least, right?
Okay.
So the label is basically, as somebody can call it, if it is just an identity matrix, right? It basically means it is a multi-class but single label. Okay. And obviously, if you see B, it is not an identity matrix. Then it is also multi-class, also multi-label. So what is happening is row 1, right? Sample 1 is being labeled with 2 values. Okay. And sample 2 is also being labeled with 2 values, and sample 3 is being labeled with 1 value.
Okay.
So that is how I see it.
Okay, no, I got it, sir. But only confusion when I saw the feature matrix, and I haven't seen these kind of examples in any of the notes, or the feature have some correlation with the labels, some understandable. So I'm confused there.
Yeah, maybe the instructors can tell whether the feature matrix even has a relevance here. I just completely ignored the feature matrix for this question.
Yes, see, for I mean, here in this particular case, feature matrix has no significance as such. But when you model, these feature matrix are used to find the predictions, right?
Right.
Yeah. So feature matrix will be something based on which you will be doing prediction.
So
for this
to
particular
identify,
question, it is not required.
to identify with
It is not required, but Abhinandan, do you see any correlation in terms of feature or label? Is it rightly categorized? Is it a kind of
so there can be a model which we, when apply on dataset A, we will get some prediction which will be like this label matrix. May not be exact, but like this label matrix, where there will be only one out of the 3 possible labels.
Okay. Any combination can be possible, right? Okay, yeah, that was my confusion.
So this is real label. I mean, actual value that you are saying. The prediction can be different from it.
Okay, thank you.
But the thing is, there will be 2 zeros and 1 1. Hello, was someone saying something?
So can we say if number of rows is nothing but the number of classes? If it is more than 2, it is multi, and in each row there is more than one. Of course, not identity matrix. Then it is a multi-class label.
So see, identity matrix. We should not say identity matrix. That's not a correct term. It's there only 1 1 and rest all 0.
So each 0 has exactly 1. Rest all 0.
Every example has only 1 1.
I think someone told earlier that a number of distinct element can be considered as class. So it's 2, so multi-class, and a number of
class you have to check over the whole data set. Okay. So when you are saying there are more than 2 class, you have to check the whole data set. But label depend on each individual training examples. Are you getting me?
So C is the correct answer here, right?
Yeah, C is. Yeah, got it, sir. If no one, I have one more question, maybe a basic on question number 11. I'm not able to get the correct answer. So if someone can help me on this, I will tell my answer. It's 0.6, but the answer is coming 0.87.
See, what is this? This is a loss function, right? So J, W0, W1, W2, and the expression is given. Now, how you will find the next steps? You will be doing WK minus alpha, and then dou J upon dou W, right?
Right.
So when you do this dou J upon dou W, what you will get? For W0, you will get 1.
Yes.
For W1, you will get 1, and for W2, you will get 1, right?
Yes.
Now you have to multiply learning rate with it. Learning rate is 0.1.
Correct.
So 0.1 into the vector 1 1 1.
1 1. Okay. Yes.
And then you have to subtract it from this 1 1 2, which was the present rate. So 1 1 2 minus 0.1 whole into 1 1 1. So it is like 1 minus
0.9, 0.9, 1.9.
1.9.
So I did have one question. There was a thing on the discourse also. Learning rate, sorry, the polynomial degree, right? The answer seems to be wrong, right? What is marked in the sheet? If you go down.
For which week is it?
No, this is the mock quiz, same mock quiz.
Okay.
The one with the various degrees, right? There's a question on various degrees.
Can you tell the number?
So question number? 16. This one, okay.
Yeah. So obviously figure 2, right? That is the lowest degree, right? But the answer is marked with figure 6 as first. So obviously figure 2 should be the least degree.
That is right.
But the answer that the mark quiz, it puts figure 6 as first.
Okay. So figure 2, figure 6.
Just want to discuss that. So it should be figure 2.
Yes, absolutely right. Figure 2 should be first.
Figure 3 definitely seems to be the end. But frankly, figure 5 and figure 1, I couldn't figure out how to really differentiate.
Figure 5 and figure 1.
At least in my visually, right? I can't really differentiate between.
Figure 1 is
I would
more
say-
smoother. Yeah.
So figure 5, I would say it is
Higher
actually
degree.
higher degree.
On the tail part, it is little bit not
Yeah. Tail as well as the head. I mean,
flat.
yeah.
These are all, I don't know how these kind of questions in the TCS ION screens will appear with
Yeah,
them.
yes.
Much
Even we
more
cannot
stress.
get this tail. That is a very valid point. You cannot see this tail in TCS laptop. You can say the monitor.
Okay.
Looks same.
Yeah, because what happened was that there are some answers, as you know, they flip figure 1 and 5, right? See, figure 3 is the last. That is, I think everybody is very clear on that, right? Because that is really learning it, memorizing that. But figure 1 and 5 are interchanged into answers, right? So it would have been really difficult to pick. I hope you don't have such questions in the quiz, because in the TCS screen, there's no way to figure this out.
So do you get so do you get the colorful diagrams in TCS Center or not?
We get, but the entire screen is so small, right? Even if
Yeah, and we cannot zoom that also.
You can't zoom.
You all will be never on losing side. That you all know, right?
No, proven wrong many times.
Okay, so
for MLF also, for if there was some confusion, we used to take into account those things, right?
Okay.
Case to case.
So
Not generalize.
just don't worry about all those things. Worry more about the syllabus and content and study well.
Okay, then anyway, just to confirm, so figure 2 is the first, that's the lowest degree, right?
Yes. I think answer C should be the correct one.
But it is not marked. If you check it, it will be marked. It will come wrong.
Okay. Okay. So I can assure you this should be the right answer.
Yeah. And I did have this lasso regression. There is a question to contact the lasso, right? I will try to do it. I haven't read it, but I was really not sure whether it's possible to calculate lasso regression by hand.
No, this question?
The mean, right?
Yes.
You can sum up and then you can sum up with the absolute value. Then you will get the lasso. Lasso is nothing but the absolute, and then you are going to sum it. Then it will come.
Okay, so I tried the ridge that came out, but this was a very undo question, right? So I didn't expect this question at all.
I think this is just 6 lambda, right?
No, I think for this the answer seemed to be not correct. I didn't get the answer as mentioned in this.
I haven't tried. Okay, what's your answer?
Because least square error comes to be 119. The lasso error should be considered 1 by 2 there, lambda by 2.
Yes, definitely.
3, 2
Okay.
plus 3
Then the sum of absolute is minus 2 here.
6 by 2, 3. So your lasso.
No, sum of absolute is not minus 3. What did you say?
Sum of absolute, like should we take absolute of each weight and add, is it?
Right.
Right. 3 plus 2.
So 1 plus 2 plus 3, it gets 6.
6 by 2, 3.
0.06 by 2, 0.03. Yeah, 0.03 gets added.
119.0.03.
No, 0.07.
Yeah, 0.07.
No, it actually it's
6, 3 to 1, right?
Yeah, 6.
6 divided by 2.
Yeah,
3, then 0.03.
Yeah.
But I wasn't able to get the right answer. So it's also an NAT question, right? So I wasn't sure whether I even got the method right.
Hello, sir.
Yes.
Sir, can you please upload the Solve with Us instructor codes?
Sure, definitely.
Sir, if possible, please do it by today, because tomorrow will be a little.
And also, like, if there is any, like in this mock, right, if there are any wrong answers, right, can you rectify that? Because when we are solving and we get stuck, it will be very difficult now to catch hold of anyone.
So Rajiv, can I request you to post a discourse forum for this one? For
There
any
have been posted,
questions,
sir. Yeah,
No,
there
no,
isn't
for
question.
any questions, I am saying any questions wherever there is something wrong, right? For the
Yes,
last
yes.
moment, at least like if you can make it correct, right? Then we will not lose our nights. Problem is there.
So,
We also-
Because we are trying, we are thinking that okay, we are losing on something, we are missing
Yeah.
something.
And let's say somehow you manage to find some logic to get the matching answer, and we believe that is the correct way.
okay. So, Rajiv, can you point out to the questions where you have this kind of problem?
No, see, like, see, I have not yet solved this, but the one like someone was telling, right, that this answer is not coming up correctly, right?
The
So I am
degree one,
telling
the
if-
degree question, regarding the
right,
different
right.
curves.
At least for them, if you know that okay, this is the correct answer, and if you ensure that this mock paper is also showing that as the correct answer, right? If like both are correct, because whenever I am going to solve it, otherwise I'll have to spend nights actually. Where I am going wrong, where I am going wrong. You got my point? That's that's what I am asking.
See, I understand your confusion that it might create. I mean, it might be some portal upload error which caused this issue. I think that that is the only explanation which is coming to my mind. Otherwise, we are pretty sure of, as sir also said, for that question of arranging degrees in increasing order, we are pretty sure what should be the answer.
No, but the thing is that, sir, actually just to add, we have asked the question. I don't think there has been an answer from the.
No, actually, that Srinivasan, otherwise I was confused with figure 2 and figure 6. I assumed that I may be wrong, so I consider that okay, 6 may be the lowest degree, but I may be the concept from my side.
But we have actually asked in the discourse forum, except that the person who asked just put clarification. They didn't say this is for the mark question. But somehow I don't think that has been answered yet. So probably you can request the instructor team to just look at the questions on the mark questions and answer them. So that.
Okay, sure, definitely. So I think it was
So this
posted
is called
yesterday.
doubt clarification. So unfortunately, the person who asked the question just titled it doubt clarification.
It is clear here, right?
Mark. They put the tag as mark. So
no, it is clear here, right? Figure 2 is degree 0, right?
Yes, absolutely.
There was someone who was saying not able to figure out between 2 and 6. Figure 6 is degree 1, figure 2 is degree
No. I was saying figure 1 and 5. Figure 2 and 6 are very clear.
Okay.
Sorry. Okay. Let me just repeat it. Figure 2 should be degree 0. The answer is incorrectly marks figure 6 as the first thing, lowest degree. The answer is wrong. So that is very clear. But figure 1 and 5, I really wasn't sure how to really figure this out.
Okay.
On the TCS ion screen, right? I was trying to visualize that screen. But hopefully, as Abhinandan said, some other person said, we will take care of it if there is a confusion.
So, sir, do you have any feedback? Do you want all figures to be in a single column? Would that help, or?
No, that will be worse because it have to keep scrolling up and down.
Okay.
We'll see, right? Let the question come. We will see. Maybe there will be some comment on the
in
question.
TCS, another pain point is your scroll bar will only work with the mouse click, not the scroll button what you have.
Okay.
That is a big pain if you were to really scroll. And it is not like if you want to lock on your scroll bar, if you move away, it will go into scroll. No, you have to stay on that thumb.
Okay.
It is very, very bad experience with all these lengthy questions.
I see. Okay. So let us know, if you want questions to be formatted in a way that it helps you on that quiz day. We are happy to do that.
Yeah. Anyway, I'm sure the quiz has been set now. So we will see how this quiz comes out. Then we will definitely give the feedback. Thank you.
Okay.
Sir, I have a doubt.
Yes.
There was this question in practice assignment 4, question number 2. I think there were 5 examples. There are so many. Can you go to the question? Then I'll be able to explain it.
Which question? Practice
Practice
question.
assignment 4, question number 2.
Week 4 you are talking about?
Yeah, week 4. Practice assignment, question number 2.
Okay. Okay, consider this one, right?
Yeah. Are we supposed to perform the matrix multiplication and then
So this one is okay. Weight factor. You can calculate the total loss. Yes, yes. Of course, why not? So this one is on practice side. Definitely the matrix is large. It could be of maybe in the quiz you can have similar kind of problem with 1 or 2 rows removed. That is expected. You are expected to do this kind of calculations.
Okay.
Sandeep, here you can use a trick because both are minus. Okay, so when you are going to add it, you will get the minus. Okay, so in all the 3 cases, all are minus. So you can consider as a 0, and all others are positive because when you are adding, it will be positive. If the both are negative, you are. But if of course if one is positive and negative, we have to do the calculation. But for these cases, it is easy because both are negative, and other 3 samples both are positive. So we can say.
Okay, the levels are also first 3
Yeah.
3 are 0. Oh, the level will be okay. There is a shortcut. Okay.
Yeah.
I didn't
If
notice
it
that.
is a
Thanks.
plus and negative, then we have to do calculation.
Nice touch. Thanks.
Swarnik, can we take
Yes.
a look at 23 and 24 questions quickly in the mock?
Of the mock?
Yeah.
Okay.
Um,
Question number 23 is this. Consider discriminant function of perceptron model this one. Okay. GY denotes the threshold function used by the perceptron. Answer the following questions. The normal distance from the origin to the decision line is. Okay.
So this should be W0 divided by norm of weight vector.
W0 divided by norm of the weight vector. Yes.
So W0 is 1 here.
Yes.
And norm of weight vector is 3. 3, right? 1, 2. Weight vector is 1, 2,
2. Yeah, right. 3.
So norm is 3. It should be 1 by 3.
It should be root 8.
The answer is prompted to be 0.35.
Yeah, so it will be 0.35 since the norm is square root of 2 square plus 2 square, not 9. Because if you see the derivation, there y equal to w naught plus w transpose x, right? So w does not contain w naught.
Oh, that was the lasso, right? Here.
So that is true for every classification case, right? When you are taking discriminant function.
Okay.
So if you remember the formula for y, it is w naught plus w transpose x, right? So w transpose doesn't account for w naught.
Okay, and similarly, for this one, it's going to be y divided by norm of w.
Yeah, norm of w without w naught.
Yeah.
Okay. Any further questions on mock quiz?
I think, sir, there is no further doubt.
Okay. I mean, we are close to 7 p.m. Would you like to go through the
No, sir, thank you.
So would you like to go through the Nitin? Are you there?
Yes, one. Is it? Am I audible now?
Yeah, much better. So since we are almost 1 hour over our time limit, what do you participants suggest? We should go with week 4 revision, or we should close?
I think we should close.
Okay, so this has been a fantastic session. I mean, you have been very enthusiastic, sticking it, till this point. At any point of time, you have any queries regarding week 4, please post it forum, discourse forum, post, and mark Nitin into it, assign it to Nitin. Then I think we should be able to look at that.
So just one question on week 4,
Sure.
question number 7 graded.
Week 4, question number 7.
Yeah, sorry, I know it's 7. You are too tired. Question number 7, week 4.
Graded question.
Yeah, graded as well. So what is the approach, that we have to separate a line equation we need this question? So what is the
plot
to approach this question?
Okay, so based on this above scatter plot, which of the following equation of the line decision boundaries classify the orange and blue points most accurately? Okay, yeah. So see, this is a toy data set. The values of x1 and x2 are not large, very small. So all you will have to do is you have to imagine some lines that you are plotting on this chart, and which one of these is actually doing the good separation.
So one by one we need to check. That is the method. There is no shortcut.
Yeah. I think I would say that is quicker than any other method. If you think that you will imagine a model and train it using some optimization procedure, that will take even larger time.
Yeah, I was trying to put some values, but it is taking time. That's why. Okay, so plotting a line is much
right. See, you can by looking at the geometry of this data set and some of the equations, you can outright remove option B and C because they are increasing in nature. Right, and you want some line which has negative slope. So only A and D are remaining, and one of these two you have to choose.
Okay, thank you. That's it. Thank you.
Sure. Okay. Thank you, everyone. Thank you, everyone, for showing this much enthusiasm and sticking with us for 3 hours.
Thank you, sir.
Thanks a lot, all of you. All the best for the quiz.
Thank you all.
Thank you. Thank you.
All the best.